Next, we will be discussing how to perform processor analyses on an Aadl model. The processor analyses invokes the same two plugins that we saw for memory analyses. These are found here. Analyze resource budgets not bound and analyze resource allocations bound. And it works similarly to the memory analyses. The first, analyze resource budgets not bound, pools capacity across the system, pools budget across the system, this time in MIPS rather than RAM or ROM, and compares the two. Analyze resource allocations proceeds processor by processor, looking at all the software components bound to each using the actual processor binding rather than the actual memory binding property that we use with memory analyses, and calculates the total demand processor by processor and reports that. We have rigged up an example that's a variant of the one that we have been using. This is called Advanced Hub. It looks familiar at first. It's got the same four threads and same two processes and digital control application, DCA.tier2, which we'll be using. Notice this reference processor property, which points to the same PowerPC that we've been using, which is clocked at 1.2 MIPS. But in addition, we have some new components, and we have a logging PC. We have a CPU board processor with 4 MIPS, and it has as subcomponents 2 virtual processors, one with a MIPS budget of 1.2 MIPS and one with 1.6 MIPS. Then down at the bottom, we will allocate the first virtual processor to these software components, the IOP process, and the BB1 device driver, more about that in a moment. And the second virtual processor will be bound to the second process, the actuator control process, and a second device driver. In addition, there is a processor, a physical processor called log, which we'll look at in a moment, which we will bind to this software component, which is also device driver, local drive 1. One interesting feature of this example, 3 different ways of implementing a device driver. The particular form of device driver that seems most appropriate if you're going to be doing processor analyses is the one for BB1. So that's the one we will actually spend a few more moments looking at. BB1 is a system, a black box system, which is just up here. It has 2 subcomponents, the device and the process. And DevBox process consists of a single thread. So if you have a device driver and you want its timing properties to be seen and considered in processor analyses, I recommend that you implement it as a system consisting of both the device, which will have no associated properties with it, maybe except weight or power draw, and the timing properties of the device driver can be expressed for the thread, and here they are here. Period 40 milliseconds, compute execution time, a maximum of 13 milliseconds, and that's all with respect to a reference processor, which is logging PC. And logging PC has a very slow clock rate, so those timings are like a snail relative to those for the main software application here, our digital control application, which we've been seeing and using all along, which has the PowerPC as its reference processor. So our 2 processes, their timings are with respect to the PowerPC. This is all said so that you understand the reports and the workflow. We're going to work directly with the workflow this time. So let's bring it up and leave it on the screen. There it is. We can bring it to the bottom of the screen there. We need to instantiate our hub. And then I can select that instance. Aha, here it is. Now, just as we could with our memory analysis workflow, we can view and edit the properties of the instance model that was created, that instance model being shown here. So we can, for instance, edit the capacity. Notice that in this view, any component that might have capacity is illustrated. So we could, for instance, edit a capacity here if we wanted. I really don't want to do that, but we could. And likewise, we can edit budget. And here are our two familiar processes, IOP and APP, and their threads. They are part of the system hub main, which is our digital control application. And then we have our three ways of representing a device driver. BB1 is superior, but here it is as a system that's composed of the device and a process that has a thread with the timing properties of interest. Second, as a system that has a subcomponent, the device. And the third, just as the device itself. So depending how much you already know about the device, one of these three ways may be superior to the other two. But we will again focus, for reasons of time, on BB1 and hub main and the two virtual processors, CPU board Core 1 and Core 2, and see what roles they play in the analysis. In the middle box here, we see the timings, and we can edit these just as we could the upper and lower box in the throughput analysis. Let's now generate our unbound report. So this is not using the processor bindings yet. That only comes with the bound throughput analysis. This is pooling across the system. And we're going to open that report, looking first at the unbound version of the report. We see at the top the summary of the processors that are used in this example. And then in the section a little bit below that, we see the virtual processors that are used. And then below that, we see the various software components, their MIPS budgets, and if timing properties allow, a calculation of MIPS from looking at such things as the thread period, the thread compute execution time, and reference processors in order to estimate the MIPS that will be needed. Again, in compositional analysis, it's this column that is preferred over this when aggregating upwards. Okay, so we know from our Aadl model, these two virtual processors were defined as subcomponents of CPU board, and the 2.8 MIPS total fits within that. The way to specify the capacity of a virtual processor is to use the MIPS budget property. In terms of software components, here's our familiar digital control application, renamed Hub Main. Notice the timings. Notice that there's a total here of 1.74 MIPS coming from the timings versus the budget of 2 MIPS for the overall digital control application. And it is that 1.74 MIPS added to the 0.3 for this device driver and the 1.3 for this device driver and 0.3 to this device driver that gives us the 2.47 MIPS. Opening now the other report, the processor by processor analysis, we see very much the same display, but now organized by processor and virtual processor. First, for CPU board, which is the 4.0 clocked processor, we see from our, might recall from our bindings here, that hub main and BB1 and hub main BB2, the IOP process and the app process, are all bound to that main processor, which has 4.0 MIPS capacity, and our 0.4 MIPS capacity second processor only has this one device driver, local drive 1, mapped to it. And so we can see this in the report. Here is everything related to hub main, and here is BB1, BB2, for a total of 2.17 MIPS mapped to this CPU board processor. And then we see that broken down further individually, virtual processor by virtual processor. But there's no report on the processor log and its single bound software subcomponent, local drive 1. Local drive 1 does appear in the other report. Here, all three device drivers appear in this report, but only BB1 and BB2 in the processor by processor report. Let's go back to our Aadl model. Recall that we instantiated system implementation hub.impl, which has these subcomponents, which consist of two processors, CPU board and log, and and hub main, our digital control application, and then three device drivers, BB1, BB2, and local drive 1. Notice that local drive 1 appears directly as a device, which is exactly what renders it invisible to the run-bound throughput analysis. And that's why we don't see it. It is better at the top level, if you're going to have a device driver appear, to wrap it around with a system, which both of these do. One more point can be made by looking to see how BB1 and BB2 are declared. BB2 is declared in terms of dev wrapper and BB1 in terms of black box. Let's look at these implementations a little more closely. Dev wrapper is a system, and the device appears directly as a subcomponent, with dev type being defined back up here with timing properties. And there is a reference processor. There's enough information to infer processor utilization. However, as we will see, that timing information is ignored by both analyses. On the other hand, BB1 was implemented as a black box of two subcomponents, as we mentioned earlier. One of them a process, which in turn has a thread, which in turn has the timing information. Notice the 13 milliseconds here. Notice the period 40. So we have 13/40ths times the speed of the reference processor logging PC, which is 400 MIPS. And if we go now to look at the capacity pooling, we see that for BB1, the timing does appear in the report. But for BB2, the timing information is not used, and only the budget that's been assigned to BB2, the device, appears in the report. And the other report works the same way. We have timing information only for BB1. This concludes what we wanted to say about analyzing an Aadl model using the built-in processor analyses, both the plugin and the workflow.